So for the first question, we're going to be talking about the differences between the temporal and spatial summation, and then why the time constant is important when talking about these summations. And so for the temporal summation, this occurs when the presynaptic neuron releases transmitters multiple times before the ESPS can fully decay. And so this basically means that the depolarization starts to build up on each other, and this is greater for slower distill events than for the proximal input. And so the keywords here are in thinking about the multiple times occurring before the ESPS. On the other hand, the spatial summation is thinking about the multiple presynaptic inputs that are firing simultaneously. So here there is, it's producing the net ESPS in the postsynaptic neuron, which is even larger than the presynaptic neuron, that could have been caused alone. And so then the keywords here are the multiple presynaptic inputs. And so the time constant here is actually important because it determines how long the action potential lasts and whether they can add up to basically reach the threshold for an action potential. If the time constant is long, then in that case it would decay slower, and this basically allows for the following ESPS to add to the previous one, which increases the likelihood of reaching the threshold and action potential. On the other hand, if the input is, or not the input, the time constant is short, then the synaptic input will decay faster. This basically means that if several ESPS occur, they won't add up to each other because the effect of each one is largely gone by the time that the next one arrives. So for number 2, we're going to be talking about what does it mean to have dendritic filtering, and then we're going to give 2 examples. And so dendritic filtering basically means, or basically is the process of weakening and enhancing or strengthening signals that go from the dendrites and travel synaptically to the stoma. And so an example of these is the CA1 pyramid neuron in the hippocampus, as it has no difference in amplitude in ESPS, as it's generated from equivocal, proximal, and distal simulation. And so for the next example, I had to search it up because I couldn't find another one in the notes, but what I did find was that there is a layer 4 stellate neuron in the visual cortex where ESPS generated at a distal dendrite arrives at the stoma with smaller amplitudes. And so this occurs unless the synaptic conductance is increased to compensate for the distance. And then I also did want to add that the dendritic filtering, I think it also can be impacted by the neck of the dendrite. So as we learned in class, if it's wider, it's able to enhance it more because it's easier to flow through, in terms of the ions. On the other hand, if it's skinnier, it's harder to flow through because of the resistance. So there's a little bit of resistance played. So now we're going to be talking about spatial buffering, their resting limit potential, what that has to do with their function, and then the high expression of connexin proteins. I'm not sure how to pronounce that, but we're going to go with that. So spatial buffering is a process in which astrocytes regulate extracellular potassium by taking the excess ions and moving them where there is high concentration of them to lower concentration. So without proper regulation, there would be too much potassium outside, so like extracellularly, and this would cause EK to increase. And so when that would happen, there would be an excess of firing of action potentials. And so the resting membrane potential of these astrocytes are actually around negative 80 MV, which is quite close to potassium's. And this is on purpose because in terms of their function, this allows it to not become excitable because of the high potassium permeability. And so this is good because this makes it more sensitive to like the ions on the outside, and so we need it to not send action potentials, but rather be able to regulate the environment around itself. And then the reason why there's high connexin proteins is because these astrocytes, the way that they function is that they send the signal through these gap junctions, and gap junctions are made up of these connexin proteins. On the other hand, regular neurons, once they go from the gap junction process to the myelination, they no longer have these gap junctions, so they have these synaptic clefts, and so they have like this gap, and so there's a less expression of these connexin proteins, as there is less gap junctions.